Right on cue. It's funny how that works. So homogeneous linear systems, but we make matrix equations out of it. So we've already talked about the parametric form of the solution to a linear system. So I think we can kind of like jump into examples, and what I'll do is just to not ignore the concept, because I know if you're, I always hated that when I was a student. It's like, well, we've already talked about that, so you know that like the back of your hand, so we're just going to move on. And you're like, oh, what if some of us don't know it like the back of our hand? Could you possibly review that? Yeah, so when we get into the actual solution, I'll point out what part of that solution represents the parametric vector form. All right? But basically, if you look at the structure of it, it sure looks an awful lot like a linear combination, right? So you have a scalar and a vector, another scalar, and another vector. Each multiplied and then the results added together, all right? So the same structure. Doesn't necessarily have to be the same variables in the same order, but it's the same general structure. So a homogeneous system is one in which all the numbers on the right-hand side are equal to 0. Okay, that's an oversimplification, but I mean, it's a good working one, because if you look at this matrix right here, you see, last column, all zeros. All right, so easy to identify visually. But what that means is that the equation was solved so that 0 is on the right-hand side. All right, so just like what I was talking about on the previous page, you might have 2x plus 3y equals 4, but I could easily move that 4 over to the other side and make it equal to 0. All right, that's all that's happening. All right, so homogeneous system is always going to be in the form of ax equals 0. All right, and one of the solutions is always going to be what we call the trivial solution. All right, so that's kind of it's kind of weird, because you're like, what does that mean? Because we're going to have trivial solutions and then non-trivial solutions, and then I'll make a comment like, oh, that one's just the trivial solution, and you'll be like, oh, okay, thanks for putting me in my place. Is that your way of saying that that was a stupid answer? Like, well, that's very trivial of you. No, it's just saying that if I'm going to take two values and multiply them, one instance in which the result could be 0 is when you're multiplying by the 0 vector. All right, so if I were to say I have matrix A multiplied by vector x with components x1, x2, x3, and I say what's x1, x2, x3, you might say x1 equals 0, x2 equals 0, and x3 equals 0. And I would say that's the trivial solution, because that's the one that would work no matter what. So then I would say, okay, what about a situation where x is some non-zero vector, but also gives a result of 0 through multiplication? All right, that's the non-trivial case, because we know we can always get to a 0 if x is 0. But can x be something other than 0 and still give us a result of 0? All right, that's the important thing, because in ordinary algebra, you have two factors. When you multiply those two factors, can't get a result of 0 unless one of them is a 0. There's no way to do it. But in linear algebra, through matrix operations, you can get a result of 0 even if the two matrices are not themselves equal to 0. All right? So very strange stuff, but that allows for, well, honestly, the topic doesn't exist without that relationship. So it allows for this lesson to exist. So, look at that. I'm just giving away typos today. Yeah, you know what? There was an example 1 at some point. It was probably a stupid example. And I said, let me get rid of that. So I got rid of it. But then never renumbered my remaining examples. So we got 2 typos here. I'll take them as 2 separate ones. All right. So, example 2. Solve ax equals 0 if A is defined as this matrix, but we do understand that if we have a zero column, ignoring that zero column is, we can do the same things, row operations on everything except for that zero column, because no matter what we do in terms of row operations, there will be no impact on that last column. All right, I can multiply, add, I can swap, I can do a scalar multiple. No matter what I do, this column is always going to remain as zero. So why do I even need to write it? So I can ignore it completely, but then I have to remember that it's still part of the equation later on. I always worry about that I'm going to forget. So what I do typically is I write the zeros on the outside, right, indicating that I don't need these values in order to perform my operations, but they're still there, right? So let's tackle this one, and really, honestly, there's not much to tackle because it's already in reduced row echelon form. All right, so we just have to write up the solution. And that's where the discussion of parametrics is going to come into play. So we know again that we're looking at matrix A multiplied by X equals 0. Matrix A, so again, matrix. And vector. All right, terminology, notation, everything's really important because people who sit for this test, they don't familiarize themselves with that. They just can't get past the fact that that just looks like an algebraic expression. And I have had people, when I ask them to solve AX equals 0, I have had people say X equals 0 because divide both sides by A, 0 divided by A is equal to 0. They ignored all the matrices and just did the algebra on that expression. And my response to that would be, well, why did I even bother with the instruction? Because if you could do that in every case, then why do we need matrices? All right. So what I want to do is take note of really what's going on here, because after multiplying A by X, I came up with this matrix. Now the last one again is equal to 0, but I do want to think about how this could have ended up being the case. All right. So I have a 3 by 4 matrix as a result of the product of A and X, all right? So I do have to think about that, but I guess that may be like overcomplicating it for now. So I'll take you from the AX to the matrix later on. For now, we'll just worry about the solution. So as it was before, we know that the first pivot value is going to, well, assuming it's in the upper left-hand corner, it's going to be associated with X1. All right, so let me focus on that for now, the parametric form. So I'm looking at X1 plus 0x2 plus 0x3 plus 2x4 equals 0. All right. You don't have to write that out in every case. I just want to do it this one time. And my reasoning for that is to really justify that, okay, so mission accomplished. I know I'm dealing with a 4-unit vector. All right. So my vector X, so I'm just going to put it off on the side here. X is equal to X1, 2, 3, and 4. All right, that's a 4 by 1 matrix. Four rows in one column. All right, now again, ignoring the 0, I ended up with a 3 by 4. All right, so through the product, that had to play out somehow. All right, so we'll get to that in a sec. So the next one is 0x1 plus 1x2 and so on. also equal to 0. And the last one is 0x1 plus 0x2 plus 1x3 plus 1x4 also equal to 0. All right, so I'm just going to go through and circle in the first one anyway the two relevant values. And you could see here that I can define my equation, my solution to the equation x1 in terms of x4. Just by subtracting from both sides. So negative 2x4. I could do the same thing with x2. Also defining it in terms of x4. I missed the positive sign there. And then the same idea for the last one. x3 defined in terms of x4, so negative 1x4. All right, so you see in each case, I'm looking at a variable being dependent upon x4. All right, so bless you. So we know x4 is free. And again, that's the same as saying x4 is equal to x4. All right. By noting that it was a 4 by 1 and that it was x1, 2, 3, and 4, as indicated by all of these variables, even if the coefficient zeroed out, I know that I'm looking for a 4-unit vector solution. All right. So when I write up this solution, I could write it in a couple of ways. One way would be to say that x sub 1, 2, 3, 4 in vector form would be equal to x4 multiplied by negative 2, negative 2, negative 1, and 1. All right, so that's one way to write it. Or coefficient of 1 in front of the x4. Another way to write it would be to say, well, x1, 2, 3, and 4 is the same as just x. Regardless of how many dimensions there are, it's still just x. So I could say x equals x sub 4 multiplied by negative 2, negative 2, negative 1, and 1. But honestly, I think it's so very important that you take note of what these values are, because otherwise, I mean, I have had, I can't even count the number of people who have indicated that it was x4 times negative 2, negative 2, negative 1, leaving off the 1 because they just didn't take note of this, and then when they went to list out their solutions, all they got is x1, x2, x3 equals. They didn't even consider that x4 would have to be equal to something too. It's also a variable. All right. So that there's that way of denoting it. And then finally, the last way to represent it well, there's really 4 ways to represent it, but this, like the last 2 ways are really the same way, just written slightly differently. So I could write x1, x2, x3, x4 is equal to 0 plus x4 times all that other stuff And like I said, the streamlined version of that would be just the same as saying x equals 0 plus x of 4 times -2, -2, -1, 1. Okay, so you might look at it and say, well, what on earth is the purpose of having the 0 vector included there? Really, it's at this point, it's more of like a placeholder. It's indicating for us that, you know what, there's not always going to be just a 0 vector. Sometimes it could be some non-zero vector, like 1, 2, 3, 8, or something like that, plus the free variable multiplied by the vector. All right? So you would have a general solution, and then you would have a particular solution. Kind of like if you're thinking in terms of differential equations. And there is, surprisingly, a tie-in between this course, later in the course, and differential equations. So this is the particular solution. And this is the general solution. All right. Now, when you're dealing with non-homogeneous, I almost said differential equation. When you're dealing with non-homogeneous linear systems, it will have the same structure, but these will have different names associated with its breakdown. But the structure itself is going to be the same, regardless of what it's called. It's still going to have the same general structure. You're going to have something in particular where it's not related to a free variable, and then you'll have something where there is a free variable associated with it. All right. All right, so then you might consider, all right, through the multiplication process, how could you have come up with this 3x4 matrix to begin with? Well, the only way that it would have worked, it would be if you were multiplying this by a 1x3 matrix in order to actually carry out that multiplication. So you'd be looking at actually, no, forget what I was about to say. They gave us the A. So I was about to talk about how you'd figure out what A was given a product, which is a subject in and of itself, but I forgot they actually gave us the A, so it's irrelevant. Forget what I was going to say.
And it says we usually ask us to have a particular solution and a general solution, or we would ask for one?
I could ask you to put it in any particular form, and then also I could be referencing those forms as part of a question. So like, given a matrix equation AX equals B, for example, which is what we're going to get to in a few minutes, knowing that the particular solution is this, tell me what the general solution would be, you know? So something along those lines. So you do need to know the structure of it and also the names associated with that structure. All right, so these other problems, they're all in reduced row echelon form, so it's really going to take on the same structure. All right, so I didn't really feel the need to go too nuts with this because the reality, and that was the example one that I deleted. It was an example where we went through the row reduction process to get it in row reduced form to then do all this stuff. And it was like, the real problem has nothing to do with row reduction. It has to do with everything with the actual solution once you have it in row reduced form.
But what do you do when the first pivot isn't referring to the x1 value?
When the first pivot, like in this particular
We're
case?
starting right off with the system of equations that's only defining x2 and x4.
So you're going to have two free variables.
Two free states.
Yeah. So that one's gonna be a little juicier, but still very manageable. And then CX equals 0. So now it should be going. All right. So the first thing you're gonna do whenever you're given a situation like this is verify that it's in reduced row echelon form, because if it's not, then you'd have a little bit of work ahead of you. All right, in this case, we're in good shape because the first entry in each row, so those are going to be the pivot values. Those are the only non-zero values in each of their respective columns, so we're good there. We're not looking at an instance where the pivot values in the last column, right? The last column is the column of 0, so it wouldn't be homogeneous if that were the case, so we're in pretty good shape here. So it's a matter of we're stating what the final answer would be based off of this. So what I'm going to do is, well, I'll write it in the detailed form first. I know it's like an unnecessary step when it comes to doing it on your own, but for the purpose of just kind of getting a good idea of where all this stuff is coming from, at least for a couple of instances, it's probably worth the time. So we're looking at 0, x sub 1, plus 1 x sub 2, plus 0 x sub 3, plus 8 x sub 4, plus 0 x sub 5 equals 0. And that will clean up kind of nicely, I guess. I mean, I guess the term nice is relative. So x sub 2 plus 8 x sub 4 equals 0. All right. So we'll do the same thing with the second row and the third row. So 0 x sub 1 plus 0 x sub 2 plus 1 x sub 3 minus 6 x sub 4 plus 0 x sub 5 equals 0. All right, so this one simplifies down to just x sub 3 minus 6x sub 4 equal to 0. All right, and then the last one, I mean, that one I don't think it's really overly necessary. I'll just do a dot 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 plus 1 x sub 5 equals 0. So you just get the actual particular value for x sub 5 that equals 0. All right. So instead of writing 0 x sub 1, 0 x sub 2, 0 x sub 3, and so on, you just kind of keep it relatively simple. All right. So cleaning it up a little bit more, surprising to think that that's still a thing that could be done. We can solve for x sub 2 and get negative 8 x sub 4. We could also solve, wrong color, for x sub 3 and get positive 6 x sub 4. All right. So, you know, looking at that, you'd say, all right, that's wonderful, I suppose. But what does that mean in terms of a parametric solution? Well, it means a bunch of things. First off, we have a free variable of x sub 4, right? We don't know what that is, but we also don't know what x sub 1 is either, all right? Everything else has been accounted for in some capacity. So we would state here that x sub 1 and x sub 4 are free variables. All right. The x sub 1 is the weird one because that doesn't seem to be really addressed within the solution, but basically irrelevance allows for freedom. All right. So it does, what this is getting at is the idea that, you know, x sub 1 didn't really work its way into the solution, but that just means that it could be anything and the solution is still going to work. All right. X sub 4 is what x sub 2 and x sub 3 are dependent upon. All right. So that could be a little iffy or a little weird in terms of constructing your parametric solution. All right. So ultimately, I want to come up with an x sub 1, 2, 3, 4, and 5. Defined in terms of just all of this. All right. Well, I guess the simple one would be to state the x sub 4 component. All right. So x sub 4 is going to be a multiplier of some column vector. It's just a question of what. All right. So we can clean it up a little bit, but we could also think of it this way. If x sub 4 is free, then x sub 4 is equal to x sub 4. All right, so x sub 4 is equal to 1 x sub 4. All right, those are the only ones that are defined in terms of x sub 4. So nothing else is accounted for here. So, we disregard all the other stuff. X sub 1, for example, it would be a vector value of 0 here because 0 times x sub 4 would go to 0, so that's irrelevant. All right, -8, 6, and 1, and then also a 0 for the 5. All right, so 0, -8, 6, 4, not 4, 1, and 0. All right, so just carry out the multiplication, and you would get zeroing out everywhere except for the relevant ones. All right. Then we would do the same thing for x sub 1. All right. So just kind of somewhere off on the side, I can make a note that x sub 1 is equal to x sub 1. So x sub 1 is equal to 1 x sub 1. But there's nothing else there. All right. There's nothing else that has a relationship with x sub 1. So I would say plus, bless you, x sub 1. And then we'd be looking at 1, 0, 0, 0, 0. And then if there's a particular value, then we'd have to account for that as well. All right, so it's just a question of, is that anywhere? Do I have it all? I think so. Because x sub 5 is 0, that's going to be a thing. I think I got it. So all that mess cleans up, kind of, sort of. But the idea being that there's gonna be kind of a mess in there somewhere. It's just a question of kind of fleshing it out. And the particular solution of the 0 vector, that doesn't have to be included particularly because it's not going to really account for anything in addition. What's that? Yeah, you could add the column of zeros, or you could skip it too. All right. So the next one, I can kind of cut to the chase a little bit here, but in cutting to the chase, I'm just going to remind myself what my columns are really telling me. This way things don't get out of hand, all right, because I confuse myself on a good day. So x sub 1 would be equal to, and I'm going to write it as -5 x sub 5. All right. The reason I'm going to do that is because the intermediate step would be 1 x sub 1, 0 x sub 2, 0 x sub 3, 0 x sub 4, and then 5 x sub 5 equals 0. So why not just negate it and bring it over to the other side? I don't have like a bunch of terms that I have to worry about here. It's just one extra term, so why not? All right, and it looks like most, if not everything, is going to be defined in terms of x sub 5, so I think we're going to be in good shape. So x sub 2 would be equal to 3 x sub 5. X sub 3 would be equal to just 0, but you could even think of that as 0 x sub 5. X sub 4 would be equal to 1 x sub 5. And then x sub 5 is the free variable, but I would just make a note that x sub 5 is equal to x sub 5. Come on. So this one ends up being a little bit cleaner. I mean, by a little, I mean a lot. It's not a mess. So we could say x, or we could say the itemized x of 1, 2, 3, 4, and 5 is going to be equal to x sub 5, negative 5, 3, 0, 1, 1. All right, and again, you could have the column of zeros to indicate the particular solution, because we have the general, so you'd want to have the particular just to build that good habit for when it's not ax equals 0. You know, it happens, so it's worth being mindful of.
And there's, the free variables are set equal to themselves, not necessarily set equal to each other, because they are separate free variables, not
Exactamundo. All right, so 5, oh, I don't need that. What is that all about? So 5 and 6 are the same idea. So again, it's just practice in writing the solution. So I'm going to put stars on those so you can play around with that. And the bottom line, you know, you're like, oh, you didn't show us the hard stuff. It's going to come up in the non-homogeneous. So that's why I feel like it would be a little bit of a waste of time to go through all of these right now. I'd rather you try those on your own. All right. But the non-homogeneous system is really just dealing with a case where the right-hand side is not equal to 0. Right? So it's like, okay, well, what do we do there? Well, there's a couple of things that we could do. One would be to actually write it so that it's equal to 0. Solution to a non-homogeneous linear system. If ax equals b is consistent for some given b, and p is a solution to the solution set of ax equals b, then the solution set of ax equals b is the set of all vectors in the form of w equals p plus vh, where vh is any solution of the homogeneous equation ax equals 0. All right. So ax equals b, we're saying it's a consistent system for some given b, and we're calling p a solution. Then the solution set of ax equals b is a solution set of all vectors in this form, so our answer is going to be the same structure, the sum of two vectors, possibly involving a free, but one of which is going to be the solution of a homogeneous system, ax equals 0. So that's our first step. So our first step in the process, again, solve ax equals 0. So really, in this case, fx equals 0. So what I'm going to do is take that matrix and get it into row reduced form. Let me see if I can get this to work for a change. Edit. A. Oh wait, no, this actually worked. Shocking. All right, so I get my matrix in. I could leave the zeros off or I could put them in. It really doesn't matter because the calculator is doing my my calculations, I just need to remember that there's going to be 0, 0, 0 on the outside. So reduced row echelon form of matrix A is going to be that. All right, so 1, 0, negative 1. 0, 1, negative 1, and 0, 0, 0. All right, so this is my RF. So just thinking forward to the test, the only time that you're actually doing the row reduction stuff by hand is the instances where I tell you to, right? Every other time, if I say determine span or solve the linear system, blah, 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 whatever the instructions are, if it doesn't say to use the row reduction techniques that we learned in class, you do not need to do it by hand. Calculator is the way to go. All right, otherwise you'd spend the rest of your life on some of these problems. All right, and still not even get it right.
Would that usually be the case? Like we could just do it by calculator instead of by hand, like the row reduction technique?
Yeah, but there's going to be I was going to say exactly 2 instances on the test where you have to do something by hand. There's one definitely where you got to take it beginning to end, and it's pretty beefy. So, you know, like you're not off the hook. I mean, that's really what it's coming down to. You know, and unfortunately, that's probably not what you wanted to hear. Just checking something here. I'm just making sure I'm not lying, because I really don't want to lie about stuff like this, because I feel like lying is a bad thing to do. It's just, you know, just not where I want to be, you know. Of course, it would help if I looked at the right file. I was looking at the final exam, and that doesn't help us right now. That's outrageous. Well, the last time I gave a test, there was like 3 or 4 instances where you had to do stuff by hand. There's no way. Like, I don't want to do that this time. I'll commit to 2 instances where you'll have to do it out by hand. I'm not promising that they're going to be easy, but I'll keep it at 2, because otherwise it's kind of overkill. I learn from my mistakes sometimes. So anyway, we have x1 minus x3 equals 0. x2 minus x3 is equal to 0. And then x3 would be equal to x3. All right. Now, any of those 4 forms that I talked about on that previous page are fine. More than fine. Completely and totally acceptable, perfectly correct. All right, I don't want to make it seem like one's better than the other. All right, so the one step that needs to happen would be, and you don't have to show it to me, but you do have to at least take note of it. x1 is equal to x3, x2 is equal to x3, and x3 is equal to x3. All right, which is the same as saying that x is equal to
x3 times 1, 1, 1, vector 1, 1, 1. All right. So x as in x 1, 2, 3, but just writing the x, it's implied, because honestly, I think it's pretty clear that vector x has to be x 1, 2, 3 because we wrote it a bunch of times already. All right. So what we did here was we violated the terms of the problem. We just did what we wanted to do. Said, okay, I know you have fx equals b, but we're going to do fx equals 0. Forget your problem. I'm going to do it my way. All right. So obviously this is not the correct and final answer. So we got to do something else. All right, and that something else would be actually solving fx equals g. All right, so that's going to be the matrix in the form of 1, 2, -3, 5. So this is not homogeneous. 2, 1, -3, 13. And then -1, 1, 0, -8. So this one is fx equals g. All right. So what we're going to do is go back to our calculator and RF this bad boy. Wrong one. Second matrix. Edit. A. This one is now a 3 by 4. And you'll see how it extends to give you one more column. Everything else is going to remain the same. I'm just going to chuck the 5, 13, and -8 in there. I said -8, but I did not hit enter. There we go. Then I'll quit out, because my previous operation should be sufficient to get me that row reduced form. So we're looking at 1, 0, -1, 7, 0, 1, -1, -1, 0, 0, 0, 0. All right, now, of course, as always, that's assuming that I typed it incorrectly. It's part of the fun, I guess. Verify. Looks good. All right. So then, something to be mindful of here. We're looking at, this is not a 0 vector anymore, just like, over here it was. So when we're actually cleaning this up to get it into the appropriate parametric form, this part is the right-hand side. So if it helps, draw yourself a little barrier to remind yourself that it's the coefficient vector, coefficient matrix, the 3 by 3, and then the solution vector together that give you the augmented matrix. So x1 minus x3 equals 7. x2 minus x3 is equal to -1, and also x3 is equal to x3. All right, little housekeeping. x1 is equal to 7 plus x3. x2 is equal to -1 plus x3. x3 would be equal to 0 plus x3, which is telling me that x is equal to 7, -1, 0 plus x3 times the vector 1, 1, 1. And so that first part of the process is really just to demonstrate to you that part of the solution to the AX equals B actually is the homogeneous solution. And that was given in the rule above, but it wasn't clear. I mean, it was in linear algebra textbook form. If AX equals B is consistent for some given B and P is a solution, then the solution set of AX equals B is a set of all vectors of the form of W equals P plus V sub H, where V sub H is any solution of the homogeneous equation AX equals B. Now, when I say it real fast like that, it sounds like much more intelligent and difficult and all that stuff. But really, all that's saying is embedded in your AX equals B, or in this case, FX equals G, is the solution to the associated homogeneous linear system. Right? You see, you have the x3 times 1, 1, 1. It's here, it's here. So one part of it is going to be the particular solution, just like it was. The P part of the equation. And then this part here takes, like I said, it takes on a different form. It's the solution to the homogeneous system. And we call V sub F. Well, V sub F. Jeez. You know, you've been teaching too many courses in too compressed of a period of time when you start putting velocity final instead of homogeneous vector. Ay, ay, ay. And then a homogeneous differential equation instead of homogeneous linear system is like linear system, linear differential equations. It's like it's designed for you to get those two courses confused. Right? I guess it would be even worse if you were a student taking those two courses at the same time. That would be pretty rough. All right. So, bottom line is, what do we do here? Reduce row-echelon form. So, like I was saying last time, if you're ever in doubt, put the matrix in your calculator and RREF it. It's just a question of what is the interpretation of that, you know? And in reality, the interpretation isn't overly difficult. It's just a question of getting the terminology right. It's always going to be coming down to the terminology. All right. And also, I think I wasn't lying when I said that by solving this problem, we were really reinforcing those problems that I skipped, that I put the stars on, because part of this was, again, going through a homogeneous system. All right. Kev, you got a question?
Yeah, I was just going to say, what's the difference between, because I'm so confused about the homogeneous and the particular solution.
So a homogeneous system is 0 on the right-hand side. And so when you're looking at the solution where 0 is not the only thing on the right-hand side, part of that result is going to be the solution to the homogeneous system. So if I had fx equals, well, in this case, the g vector, to go through this process, as part of the solution, I'm getting the homogeneous solution. All right. Then when you put that together with the particular solution related to this resulting vector, put it together, that gives you the entire solution for this linear system. All right.
So the fx equals 0 was just a part of.
Yeah, it's kind of the lead up to this. Because really, if you think about it, the general part of it, that's why in the previous page I called it a general solution, because you have fx equals 0, that allows for the vector on the right-hand side to have a basis of the 0 vector, which is where everything starts. So I know that if I have a solution for a linear system that incorporates 0, I know that since every vector has to start at 0, I know that that's going to springboard out into every other possible solution, because every solution has to start at the 0 vector, otherwise it's not a vector.
Is there a reason for the general solution that you made the free variable one? Or is it
Is there,
like a particular reason that you've made the free variable one equal 1?
the free variable is, it just has a coefficient of 1, only because if I'm just looking at coefficients of the variables, once I say that x3 is equal to x3, x3 is, it's the same as x3 is equal to 1 times x3. So since we need a coefficient for each variable on the right hand side, the natural coefficient would be 1. All right, so in this case we have, and again, the little, it's not, I wouldn't call it a shortcut, but it's just an organizational strategy. All right, so it just becomes a little bit easier to see what's going on when you do it this way, in my opinion. So x sub 1 equals 7x sub 4 minus 2x sub 5. Personal preference, I like to do it this way, but if you want to write it out and then move some things around, that's fine too. And you know what? I'm also kind of running the risk that it's the pivots that I want to define my solution in terms of, which is typical, which is often, most likely, even I would say 99.9% of the time the case, but every now and then it's not. So maybe there's a more convenient way to do it, but odds are if you do it this way, it's going to do you well. That was not good grammar, but we're getting in the habit of letting that sort of thing slide with me, I think. I know you have tests on your mind, but I do have to share. I was talking to my son today, and we were talking about like just niceties with other people, and like I realized that I never do this, which is really bad. Like I asked him, did the teacher ask you how your weekend was and things like that, and then he would say, yeah, no, blah blah blah, and then it turns out, I'm trying to tell the story really quickly because we're focused on a test, but he said that they talk about it with each other, the students, and he'll ask another student, well, what'd you do over the weekend? And they'll say, nothing. And then he'll say, well, that's not possible. He's 9. So he's like, that's not possible, because even the act of doing nothing is doing something, right? I mean, you're talking about like doing nothing. It's a verb. Like when you're not, if you're doing nothing, you're still doing something. And I was like, man, you're 9 and you actually know grammar better than I do. Like, it's crazy. Maybe it's because he's getting tested on it, like on a weekly basis. And I got tested, it didn't matter. So I'm looking at the x sub 2, and I see a negative x sub 4. I don't see an x sub 5, but everything else has an x sub 5 in it, so I'm just going to go ahead and pop that bad boy in there. So plus 0 x sub 5. All right. Now, x sub 4 and x sub 5 have to be our free variables. All right. So a slightly more structured approach than the mess I created on the previous page. So x sub 4 is the free variable. So I'll make a little note here that these are my frees. But what that means is x sub 4 is the same as x sub 4. So 1x sub 4. But I could also think of it as 1x sub 4 plus 0x sub 5. And for x sub 5, I could think of it the reverse. 0x sub 4 plus 1x sub 5. And in that way, I think it's a little bit easier to see that x should be x sub 4 multiplied by 7, -1, -5, 1, and 0. Assuming I copied numbers down correctly. Plus x sub 5 -2, 0, 4, 0, 1. And then if you want, you throw in your particular solution of the column of all zeros. That's associated with the homogeneous case. When we go to the non-homogeneous case, it's going to be the same stuff. It's just you're going to have a column that's not all zeros, right? So you'll learn to just kind of make the adjustment. All right, so then we get the craziest one out of all of them. Got some pivots here. And again, x1, 2, 3, 4, 5, 6. Yikes. X sub 7. That's gross. All right, so x sub 2 is going to be equal to positive 5 x sub 4 minus 5 x sub 7. All right. I don't have any pivot values in the x sub 1 column, so I know x sub 1 is going to be one of my frees. I could just jump right into x sub 1 is equal to x sub 1, but I'm going to leave it blank for a sec. All right. X sub 3 is going to be equal to -7 x sub 4 plus 3 x sub 7. X sub 5 is equal to 0, among other things. You know, 0 x sub 4, 0 x sub 7, 0 x sub 1, all that good stuff, but for now, just 0. X sub 6, I'll do that in blue actually, because x sub 6 and x sub 6, we actually have something, so I want that in the same color. It's x sub 7 that we're not gonna. So that's 1 x sub 7, and then x sub 7 is a free. All right, so these are my two frees. All right, and what that means again is that x sub 1 is the same as x sub 1. X sub 7 is the same as x sub 7. Even more so, if I'm going to have a proper solution, I want each one of these variables to be accounted for. So x sub 2, I want to be thinking of that as 0 x sub 1 plus all this stuff. Same thing with x sub 3, x sub 5, x sub 7, and then x sub 1, I want to incorporate the x sub 4 and the x sub 7. So this is like a way station before I get to my final answer. So I'm going to rewrite x sub 1 is going to be 1 x sub 1 plus 0 x sub 4 plus 0 x sub 7. X sub 2 is going to be 0 x sub 1 plus 5 x sub 4 minus 5 x sub 7. X sub 3 is equal to 0 x sub 1 minus 7 x sub 4 undo. I think if I have it too small, it doesn't pay. Yeah, that's the issue. Plus 3 x sub 7 So x sub 5 is just a plain old 0. Okay, so 0 x sub 1, 0 x sub 4, and 0 x sub 7. Oh, I missed the x sub 4. Where's my x sub 4? Well, it's free. I'll chuck that in somewhere. All right, x sub 4. We're going to have 0 x sub 1 plus 1 x sub 4 plus 0 x sub 7. X sub 5 is the one with all zeros. X sub 6 is equal to 1 x sub 7, so 0, 0, 1. And then x sub 7 is just the x sub 7, so it's the same thing as x sub 6. Alright, so now it's just a matter of stating our final answer. Now there are plenty of steps that you can consider skipping. It's just if you're organizationally challenged like I am, then you may want to avoid doing that. So 0, 5, negative 7, 1, 0, 0, 0. X 7. Then we have all this. All right, so we have a solution that's dependent upon 3 free variables. All right, so I don't know. There's a lot going on with that, but it's crazy to think that you're actually given the solution already. All this is just getting it into a particular form, because you didn't have to do any of the row reductions. You didn't even have to come up with the matrix itself that had to be row reduced. It was just, here's the homogeneous system in matrix form, put that solution in parametric form, and in doing so, you're like, wow, there's a lot more to this than maybe one might otherwise think. But it's really not that bad as long as you have a procedural approach. Right? Maybe you don't have to be as detailed. I mean, you saw a previous page. I kind of just made little notes here and there, and that got the job done. But it's when you're structured like this, you're less likely to miss something glaring. Yeah. So. And the moment you've all been waiting for. Word problems. That is nothing. It's mere child's play. Yeah, it's really just intimidating to look at, but really, okay, I'll just kind of spoil it. Once you come up with your equations, you're going to put it in matrix form, and then you're going to row reduce by typing it into your calculator and hitting rref. So, same idea. When in doubt, put it in reduced row echelon form, right? And then from that, you'll get the actual value. So, what's the difference between this and all the other problems that we were doing? Okay, well, instead of x1, x2, x3, we have p, m, and g. That's the only difference, right? And a little bit of context associated with it. So, actually, the benefit of a problem like this is that you have a fighting chance of being able to interpret your answer. All right, but the solution of this is what some call a vectorless solution, and so what that means is that, you know, if you were to actually graph the solution, you know, you could write it in vector form, I mean, I suppose you could write anything in vector form. But if you were to graph it, write it in vector form and then graph it, that diagram wouldn't really have a whole lot of meaning, right? Because what does a vector related to 5 sheets of craft paper, 2 boxes of markers, and 3 glue sticks really mean? You know, I don't know what the craft paper axis, the box of marker axis, and the glue sticks axis would have to do with 3-dimensional space. All right. So you could visualize it in the form of a graph, but that graph is not going to have a whole heck of a lot of meaning. All right. So we have Jesse, Maria, Charles went to the local craft store to purchase supplies for making decorations for the upcoming dance at the high school. And of course, they were thinking matrices and, you know, linear algebra when coming up with all this stuff. Jesse purchased 3 sheets of craft paper, 4 boxes of markers, and 5 glue sticks. All right. So right back to algebra 1 here. 3 sheets of craft paper, which is P, 4 boxes of markers, and 5 glue sticks. All right. And then, of course, you know, just because no worksheet would be complete without a typo. Just like I like to make sure I have at least a good, juicy typo on every page of my packets. P does not actually represent the number of sheets of craft paper because they've already told us that. We need the unit price, the cost. The unit cost. I really need somebody to submit this typo for me because I'm pretty sure that I've had to make this adjustment every semester for the last at least 10 years. So, bill before taxes was $24.40. Maria spent $30.40, so I'll just put that over here. When she bought 6P, 5M, and 2G. And Charles spent $13.40, bought 3P, 2M, and 1G. All right. Now, personally, when I'm dealing with a word problem like this, because you know it becomes a little too rote, a little too mechanical. When you honestly, this whole course becomes a little rote and a little mechanical. It's kind of not fair because you, on your end, you develop good habits, and those habits are related to the procedures. But sometimes it's very easy to lose sight of like what it is you're trying to work through. And so I know that you could take the coefficients and put them all in a matrix, row reduce it, and you'll know what the P is, the M, and the G are. But structurally, I think you need some kind of transition in order to get there, all right? And that transition would be 3, let me actually do it in a completely different color. 3, 4, 5. 6, 5, 2. 3, 2, 1. Multiplied by PMG. And you know, you can verify through the multiplication process. If I take this row, multiply it by that column, 3 would get multiplied by P, 4 by the M, 5 by the G, all added together. That would give us this. It should result in the total cost vector. that sounds fancy, total cost vector. All I did was I took the name for what it was, like in common sense terms, and then threw the word vector on at the end. All right. Be like, go over to Captain Lawrence and you look at the menu, because they always have like the different types of beers, the cost, and then they have my favorite piece of information, the IBUs. I can create an IBU vector. International bitterness units or something like that. But basically it's like how bitter the beer is. Now if they had that for everything, that'd be great. Imagine going into like the produce section in the supermarket. You're like, I like fruit, you know, but I don't want it to be too tart. So they give you the IBUs on each one of them, and you're like, oh, okay, this is perfect. I like the low IBUs and nice healthy fruit, and it's not going to be too tart, you know. So you can do that for everything. Have it for like teachers' personalities. IBUs. Oh, your IBUs are really off the chart. You must be like a real nasty person. So anyway, those would all be represented in vectors because they're common variables, or the common units allow for them to be grouped together. All right. But then ultimately, what are you doing? You're taking all this, putting it in your calculator, and hitting rref. All right. So 3, 4, 5, then 24.4, 6, 5, 2, then 30.4, 3, 2, 1, and then 13.4. All right, so matrix, reloaded. So 3 by 4, which is what I want. So 3, 4, 5, 24.4, 6, 5, 2. And I don't want anybody to think, you know, like my reference to Captain Lawrence, you know, it is a beer reference in math class. It might sound inappropriate, but like, it's totally okay. I mean, I support all of the different places, not just Captain Lawrence, like Yonkers Brewery, also a good place. Brooklyn, there's Dogfish, which is down in Delaware. So that's, you know, like a bunch of different places. So I don't want you to think that I'm just supporting one place. I mean, it is a local place, so support local business, of course. But yeah, the appropriateness of it, I wanted to make sure that I was addressing that. You know, it's like I'm equal opportunity when it comes to that stuff. All right, anyway. rref. I hit the wrong thing, cripes. The rough part is through this whole demonstration of me putting it in my calculator and all that stuff, you all have been done with this like for minutes now. I'm the slow poke. All right, so we have this. I'm gonna get a little lazy and do it this way. Just pop it in there. Oh, copy doesn't work. I have to save to. Oh, I guess I could just dump it on your phone. That'll work. Wait, what happened to my? Yeah. Yeah. One for everyone. Wait, this is it, right? I just put it in the. Well, I didn't want to post it on my iCloud, but it's usually. Oh, I just hit done. That's why, and it'll ask me to save the photo. Okay, like I zigged when I should have zagged.
He was about to change his options.
It's like, get me out of here.
Yeah.
FYI, in case anybody's wondering, that part of this stuff doesn't show up in the videos ever. Not that it was like personal information or anything, but it's only what is being plugged into the this particular app. Oh, crooked. Come on, you son of a gun. There we go. Hugh Jackman. So we have, and again, and so like I was saying before, like this is a vectorless solution. So we learned all about homogeneous vectors and all that stuff. It's like, yeah, you could write this as vector p(mg), I think it was, is equal to vector this, that, and the other thing, but what does that tell anyone? Like if somebody wanted to know how much all this stuff costs and you showed them a vector with these values, they're not going to be thrilled, right? So what you want to do, they gave you the question in words, you're going to give the answer in words. So it's paper, you could go paper markers and glue sticks if you want, but unit cost, unit price if you want. That all just depends on perspective. It's cost to one person, it's price to another. So paper, $1.75. Marker, an outrageous $3.60 for a single marker. You're out of your mind. Glue stick. All right, 95 cents, I can live with that. For a single sheet of paper, $1.75. Now this is craft paper, so I don't know. It could be pretty fancy stuff, and if that's the case, maybe you do pay $1.75 for it. But it better be some piece of paper, I'll tell you that. Because even a dollar bill isn't worth $1.75, and that's a piece of paper, as you all know.
That's the final answer.
That is your final answer, yeah. And again, what do? RF, write down our answer. But the structure of it is really the important thing. Now, admittedly, some other situations will be more complicated. I would not categorize number 2 as one of those situations. So I'm going to pop a star on that one for you. Hold on, let me just double check something. Yeah. All right. We've got some phone calls going on. The rates per minute for these calls vary for the different countries. Use the information in the following table to determine the rates. All right. So they're telling us to let C represent the rate for calls within Canada, U represent calls to the United States, and B represent the rates for calls to Brazil. All right. So we have to kind of set this up, but really the table sort of kind of gets you going in the right direction, right? Because we have the monthly charges, and we also have the variables associated with those monthly charges. So I could just jump right to it in this case, because the time multiplied by the rate is going to give me the charges for that subset of the linear system. So I could even just chuck the C's in here as soon as I get a pen going. And then put some plus signs, some equal signs, and this is what my linear system would look like without rewriting it all. And in fact, I want to actively avoid rewriting it all, because if I do, then I'm just rewriting it for the purpose of pulling out all those coefficients again anyway, to make the matrix that was given to us so generously as 90, 70, 50. All right. I'm gonna write it as a linear combination though, just to kind of force feed a little bit of review of that concept. So C times 90, 70, 50 plus U times 120, 100 and 110 plus B 180, 120, 150. And then that's going to be equal to 252, 184, and 206. It's in this moment that I realized that wherever I stole this problem from, whatever textbook, I think they might have been Cubs fans. Yeah, it's like subliminal. It's kind of like hidden in there. But there it is. It's like staring at me now that I see it. All right, so the matrix. Well, the matrix is exactly what was given to us initially. And so that's what's getting typed in. Pause it. All right, so into the matrix, edit, we got a 3x4. No, I want to go up there. 3, enter, 4, enter. And then I can start typing in this jazz. Double check, make sure I typed it all in correctly. I think so. Alright, quit out of there. Math, reduced row echelon form, matrix A. And so we get that. Alright, now that may be a wonderful set of solution values, but maybe not. I'll take a look in a sec. We're talking about charges. So, or I'm sorry, a rate. Once we get a sense of the units, which I kind of glossed over, we'll have a better idea of whether or not this answer makes sense. But the one thing, normally I would just math frac that for the simpler answer, which would be a more, I don't know, friendly looking answer in terms of what I'd have to write down. But since we are talking about rates, I guess the decimal values make sense. All right, so the rates per minute, 40 cents, 60 cents, and 80 cents. All right, that doesn't sound outrageous. All right, made phone calls within Canada to the United States and to Brazil. Okay, well, I mean, I'm not an expert on this in terms of what the rates ought to be, but it does seem to make sense that the calls within Canada, if he's in Canada, should be cheaper than United States and also Brazil. So, I mean, it's a very outdated question, but if you're just defining it based off of distance away from your current location, it would make sense in that regard. So Canada is 40 cents per minute, so calls to the US, 60 cents per minute, and to Brazil would be 80 cents per minute. All right. Now, a lot of this stuff I wrote down for instructional purposes. You know, I'm just trying to give you a detailed sense of the thinking. But really, if you're doing this on a test, you already have the matrix. Now, it is possible that a table can be given to you in a different kind of order, and you have to pull out the relevant pieces and reorganize and things like that. But as it is constructed in this case, this is the matrix that you want. So we're good to go there. Once you RF that, I need to see that, but then your final answer. So really on a test, final answer is really the work, right? Because I don't need to see a new matrix, it's already here. You show me the RF, which gives the answer. So you're really writing this and that. So basically you're just writing the final answer essentially with its own justification, and that justification is the fact that you use reduced Row-Echelon form on your calculator. All right. And I know that RF means that, right? So if you write RF, then I know that you're using the calculator approach. You don't have to say I did RF in the calculator. Because if you did RF by hand, you'd have like 15 to 20 different matrices written out, and I think it would be pretty obvious. And in fact, if you wrote RF by hand after writing 15 separate matrices out, I'm going to have a conversation with you about number 3. Number 3 is just straight up a repeat of number 2. Different numbers and stuff, but not really worth getting into. Number 4 is good, so you could pop a star on that one, but I would also understand if you're like, yeah, not going to do it because that one looks like conceptually a repeat of number 1. And it really is, but, you know, you still haven't practiced one on your own, so it's not the worst idea in the world to try at least one where you're like, I know what I'm supposed to do. So I'll put redundancies. All right, yeah, so on the next page, the number 3 was the duplicate. Was it which one was the duplicate? Because I just crossed out something.
5 was the one that was in the wrong unit.
5 was the wrong crossed out.
And number 3 was signed.
Yeah, thought so.
I thought I crossed out number 3 because it was like the same question as number 2.
It was worse.
It's worse than the same?
It's worse than 2.
Well, it sounds exciting. I don't remember now. Because I've crossed it out like every semester. Yeah, okay, well, yeah, Carlos called within Canada to the United States and to Mexico during the month of December. So you see how creative I can be with this. Instead of Brazil, I can go with Mexico. I can go to like, throw in a Caribbean country. All right, the charges are 28 cents per minute. Within Canada, 30 cents per minute to the U.S. and 84 cents per minute to Mexico. If the following conditions are applied, his total bill for the month was $90.96. He talked twice as long to Mexico as he did to the U.S. And the total number of minutes spent talking with Canada and Mexico was 122. All right, so unfortunately not given in table form, but that's okay. They're saying X, 1, 2, and 3 represent the number of minutes. In each case, we're looking for the number of minutes rather than the cost per minute. All right, previous question, we were looking for cost. Now we're going the other way. All right, so we'll get our setup here. And, you know, it's all, I mean, all the charges are detailed in there, so I think we'll just kind of skip the part where we'd write it down as cost per minute to Canada is this, that, and the other thing. All right, so total bill for the month. All right, so that's going to be Well, we have x1 is at 28 cents, so 0.28 x1. Then 30 cents for US, so 0.30 or 0.3 x2. And 84 cents to Mexico, so plus 0.84 x3, and that should give us $90.96. He talked twice as long to Mexico as he did to the US. All right, so x2 okay, so whatever the amount of time for US was, it was double that for Mexico, so double the US and you get Mexico. The total number of minutes spent talking with Canada, which is x1, and Mexico, which is x3, would be 122. All right, so we just want to get this in matrix form. Now, you can clean it up a little bit, but the cleaning up part is just to get it into an appropriate form. So the form is going to be so that we have all the variables on one side and the constants on the other. So 0 x1 plus 2x2 minus x3 would be equal to 0. And for the other piece, I think we're good there as long as you know that the coefficient of x2 is going to be 0. All right, so 0.28, 0 and 1, 0.3, 2 and 0, 0.84, negative 1, 1, and then the 90.96, the 0, and the 122. I'll double check a Ruski here. I think so. Yeah, what's up?
For x2, is there a reason why we went with 2 instead of 0.6?
Say that one more time.
So it says that the price per minute was 0.3 cents, and they doubled it. So shouldn't it be 0.6? Or
And they doubled it? Did I miss that?
Double the number of minutes, not
Yeah,
okay.
because that sounds like the kind of thing I would miss. All right, so new matrix, still 3 by 4, so that's good news. Well, it's not really. I just felt like I had to say something. It's news. Good, 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 good. Yeah, here goes nothing. Well, our numbers are not ridiculous, I guess. So that's something. He talked twice as long to Mexico as he did to US. That checks out.
You're right.
Same answer? Alright. Cool. Yeah. I mean, because, like, as far as a check is concerned, I didn't want to really get into the first one, but these are easily verified, I think, because you can just verify that Mexico is double US, and that if I took Canada and added to Mexico, I get 122. That seems to bear itself out. So, pretty solid. So 42, 40, and 80. And there it is. So really it's just a matter of muscling your way through the setup of it, because after that it's the same as every other problem. Just plug in your calculator and go from there. All right. So the next one, Tracy, Danielle, and Sherry bought snacks for a girls' sleepover. They each bought the items shown in the following table at the local convenience store. All right, number of bags of potato chips, number of liters of pop. Jesus Christmas. I gotta stop like blindly just copy and pasting off of websites and stuff. Number of liters of like soda or something, like, I don't know. You know what? If I'm gonna do it, I might as well do it. Fanta. Like, whatever. I mean, just something. Pop. What is this, the 30s? Everybody get a bottle of pop. So we want the unit price of each snack purchased by the girls. All right, so I'm going to let X1, 2, and 3. X1 is the unit price for chips. Got to define your variables, unless they define it for you like all the other problems, but in this case, it doesn't seem like they did. Fanta. And chocolate bars. All right, so X1, 432 plus X2, also 432, or 423. So same numbers, different arrangement. 6, 10, 4. And then we have the 21, 20.88. For the love of Christmas. And then 13, 17. All right, so for this, you can just jump right to the calculator, because once you have it written as a linear combination, then it's the same as writing it in matrix form, or not really, but it's the same in terms of like how you're going to approach things, you know. All right, double checking. Looks good. And so we get that, which I have no interest in writing, so. Gonna have a lot of these saved in my camera roll. Alright, so unit price. You have chips, $1.98. You get the pop. $1.47, and then you got the chocolate. Step right up, ladies and gentlemen. Get your pop over here. No.
I don't know why I do stuff like that. So that's the unit price. Now,
It's a little iffy on exactly whether or not that falls
into the spirit of the definition of unit price, because they don't always define a single unit as a bag of potato chips. It's usually in terms of ounces or pounds or something like that. All right. So, but that's a general idea. When we're talking about the unit price, you're talking about the price for a singular. All right. So it's just in this case we're defining it as number of bags, number of liters, number of chocolate bars. But if you're doing it by ounce,
That's why when you go to the supermarket and you're deciding whether or not you want to buy like a 2-liter of soda versus one of those the specials, the 12-pack of soda, the box of them. You know, you look at the price and it's like the 12-pack's a little bit more expensive, but if you look at the unit price, it may turn out that you're getting a better deal for something like that. So, is it necessarily a good idea to go with the 2-liter as opposed to, I don't know. But this is an application of that particular idea. All right, just in simple terms, because I don't want to go too crazy with it. Chemistry, nightmare. Physics, boom, I got you for that. All right, so, I mean,
You want to talk like hydrostatic force, you want to talk electricity, I do it all. All right. So find the general flow pattern of the network shown in the figure. Now, a network, it could, you think network, you think computer science and things like that. But a network is just talking about a flow into particular nodes, right? And so those nodes could be intersections of streets, all right? So if you're thinking about, like, how do they determine when to make the light turn red and when to turn green, like what the intervals are, it's actually coming from concepts in linear algebra and graph theory and things like that. All right, it could be electrical currents, right? If you're talking about, like, for example, a 3-way switch, if you're thinking about a situation where you have like 2 light switches that are going to a single fixture, like, how do you orchestrate it so that the electricity is going in and out in the right order, right? These kind of situations really diagram that out. And in fact, if you ever looked at an electrical diagram, it's going to look an awful lot like this, all right? And in fact, we will do electrical diagrams before the course is over. So anyway, what we're going to do is we're just going to talk about equilibrium at these 3 points, the 3 nodes, A, B, and C, and
just identify the direction. Directions going in and out of the node. All right, so at A, I can see that I have X coming into the node, X4 also coming in, and X2 is going out. All right, so the first decision you have to make is defining in and out. All right, so I'm going to let in be a positive direction. And out would then be a negative direction. All right.
Now, context is the driving force behind a lot of this stuff. So this is a contextless situation. But if I tell you that this is foot traffic, like you're talking about, pathways and foot traffic, maybe you wouldn't define in as being a positive thing. You might say, well, we're gaining all these people, it's going to be a crowd. That's a negative thing. You might call that the negative direction. But bottom line is, in or out, one is positive, one is negative, you take your pick. All right, so at A, what I'm getting is
that we're going to be looking at it because it's an equilibrium. It's got to be a zero sum. I'm going to have x1 plus x4. I'll do my ins first. Minus x2 is equal to 0. All right.
But is like, you said x2 is
X2 is out, that's why it's a negative. All right, so I did my positives first and then my negative. I'll reorganize it in a minute. All right, so that's at node A.
And that doesn't violate whatever the line before saying, if you assume that the flows are all non-negative values?
Correct, because the flow itself will come out in the wash as either being positive or negative, and it'll work out. All right, and so B, we have x2 coming in now. All right, so that's a positive x2 based on my definition there. x3 is coming out, so minus x3. And then 100, that 100, it's not a variable, it's just a set quantity, but that's leaving node B. All right, so it's like if you're thinking about a theme park or something like that, and you have a courtyard or you have like a popular vendor or something like that. This is the flow of foot traffic coming in, coming out, but ultimately at the end of a certain period of time, you're gonna have 100 people leaving on this pathway, all right? And that's based off a data collection. But that 100 is in the out direction, so minus 100 equals 0. And then the last node is at C. So here you have 80 coming in, so it's a positive 80. You have x3 coming in, so plus x3. And then you have x4 going out, so minus x4, result is 0. All right. So I have 3 equations, but 4 variables. Now each equation doesn't contain all 4 variables, but 3 equations, 4 variables, which means one of them is going to be a free variable. All right. And that should have happened in the chemical equation one, but because I botched something early on, it didn't play out the way I wanted it to. You know, the correct way. Chemistry. So x1 minus x2, I'm going to put plus 0 x3 plus x4 is equal to 0. Then 0 x1 plus x2 minus x3 plus 0 x4, also 0. And then 0 x1 plus... I missed 100? Where's my 100? Ah, cripes. Equals 100. Because I'll just move that over to the other side. Just so I have all my variables together and all the numerical values together also. 0x2 plus x3 minus x4, and then on this side it'll be a negative 80. All right. So 1, negative 1, 0, 1, 0, 0, 1, negative 1, 0, 100, and then 0, 0, 1, negative 1, negative 80. And then we can pop this in. This is a 3 by 5. So So 1, negative 1, 0, 1, 0, 0, 1, negative 1, 0, a hundo, and 0, 0, 1, negative 1, negative 80. Double check a Rooski here. All right, let's hit enter on that to make sure it's locked in. Good. And we get that. So I won't be lazy this time. I'll just write it in. 1. Oh, maybe I'll write it in, assuming it's going to let me write it in. Ref 1, 0, 0, 0, 20. 0, 1, 0, negative 1, 20. 0, 0, 1, negative 1, negative 80. All right, so that's my reduced form. But we do want to put it in the appropriate solution form, in my opinion, that is most conveniently the parametric form. All right, so we'd have x1 equals 20, x2 minus x4 is equal to 20, x3 minus x4 negative 80, which implies that x4 is my free variable. Let me get rid of that. So x1 still 20, x2 20 plus x4, x3 negative 80 plus x4, x4 is going to be x4, but we will have a condition on that, which I'll talk about in a sec. All right, and actually, let me make a slight adjustment here. Let me make that 0 plus x4. Cripes, come on. Oh, my pen just turned off. It's running out of battery, that's why. And so while I'm at it, I might as well take my x1 is just a solid numerical value. x1 is equal to 20, but I could still write it as x1 equals 20 plus 0 x4. All right, so x is going to be equal to 20, 20, negative 80, and 0, plus x4 times 0, 1, 1, 1. However, the condition, because of that whole non-negative thing, we want a non-negative flow. If every node is going to show a non-negative value, the condition is that x4 has to actually be greater than or equal to 80. Otherwise, x3 would be less than 0. Let me fix that symbol. All right, so by the laws of linear algebra, x4 is a free variable. It could be anything, but by the context of the situation, because we're only looking for the activity in and out of the nodes to produce a non-negative value, it's telling me that I have to orchestrate this so that every instance x1, 2, 3, and 4 will yield a non-negative value, in order for that to happen, x4 has to be 80 or more, right? If not, it would produce a negative value here, and so that node would be, well, if you really contextualize it, the net flow within that node would show a negative value, all right? So depending on what you define as negative, that could be a problem, all right? So if negative is inward, then that's saying that people are like still in the theme park after it's closed, all right? If it's in the outward direction, you're saying more people have left than were there to begin with, which doesn't make sense either, all right?
So the thing that tells us that that score has to be greater than 80 is the fact that it's like a circuit, and a circuit can't have like a negative flow.
That, and, you know,
Oh,
and also said it this one time, but the reason why it said it is because of what you said.
Okay.
Right. All right. The wrong unit. Okay, I have that. All right. The moment you've all been waiting for. Back to that chemistry problem that I screwed up last time. God, I hate chemistry. There's at least a 20% chance I'm going to get it right this time, though. All right. So we have aluminum, oxygen, and carbon. And that part I didn't mess up. You still have aluminum, oxygen, and carbon making up each vector. All right. All right, so single atom of each. All right, but if you're going to balance the equation, you do need to know how much of each molecule. This I know is a molecule, that's a molecule, but this is just an element, right? But I suppose it's following the same idea. How much of each of these would I need in order to keep it balanced? All right, so regardless of whether or not I know what the hell I'm talking about in the chemistry sense, the math part should be okay. All right, so for and we'll just look at it a piece at a time. So we have this molecule, compound, something, I don't know, words. All right, so I don't know how much of this first one I need, but that's kind of the point of this whole thing. So that'll be my weight. I do know that I have 2 atoms of aluminum, 3 atoms of oxygen, and no carbon. For the second one, I know that the only thing I have is carbon, which means I don't have any aluminum or oxygen, but I do have the carbon. If it's going to be balanced, then the weights for the other 2 would have to balance this out. With the idea being that, you know, if I could figure out what x, 1, 2, 3, and 4 are, not only will I have the structure that allows it to be a balanced equation, but I'll also have the means by which I can set up a linear system and come up with a solution using my calculator. All right, so I have 1 aluminum and nothing else. And then for the carbon dioxide, I have no aluminum, 2 oxygen, and 1 carbon. All right. So we have matrices on either side of the equation. I mean, I could make it into a 3x2 on the left and a 3x2 on the right, but properties of equality allow me to bring it all together and use something that we learned in the last part of the unit, which is the concepts involving the homogeneous cases. All right, so let me just get rid of this for now. Bring it back in a minute. Just need some writing space. So we're looking at x1 Let me just bring it in a little bit more. X2 then minus x3 minus x4 all equal to 0 vector, making it homogeneous. All right, and so we have a linear combination, and what we're looking to do is make this, or determine the weights that would allow the 0 vector to be the resulting vector. All right, now it is possible that you could trial and error your way through this, but I do not recommend that. One thing that you would want to do is create the sum here by distributing through the negative. So I'm going to make this a plus, but then multiply my vector by a -1. Do the same thing here. Obviously, multiplying the 0 by a -1 doesn't do anything. All right, so 0, -2, -1. So that it's ready to rock and roll in matrix form: 2, 3, 0, 0, 0, 1, -1, 0, 0, 0, -2, -1, and then since it's homogeneous, I could put the zeros on the outside, or I could leave the zeros on the inside. Nobody's losing any sleep over that kind of thing. All right, so, you know, if you, because I mentioned it before, and I really meant what I said, is that once you incorporate the calculator, there really is no difficulty between the homogeneous and non-homogeneous cases. So if you want to tackle the homogeneous cases exactly the same way as the non-homogeneous, that's perfectly fine. All right. So 3 by 5 now, or 3 by 4, and just remember that you have a column of zeros on the outside. Either way. So 2, 0, -1, 0, 0, 3, 0, -2, 0, and 0. Just doing a quick double checkaroo. And then reduce row echelon form. And look at that. Oof, ah. That's pretty nasty. All right, let's math frac that. Math, enter, enter. At least get some decent looking fractions out of it. Math, enter, enter. So hit the math key.
Same thing as the.
Yeah, it's like, and then hit option 1, frac, and then.
That's like a life-changing.
Little something I bring to the party. Yeah, I mean, the decimals weren't terrible in this case. I think they would have been all right, but the idea that we don't have to deal with those decimals is just wonderful. And also, you know, the obvious situation is when you have cases that involve decimals that aren't as neighborly as these. So, you know, what do you do in those cases? Math, enter, enter again, and hope for the best. All right, so. Oh, teensy tiny. Come on, get in there, you son of a gun. All right, there we go. Oh, pen turned off. Here's my RF. Now I just got to come up with a solution out of all this. So we have x1, 2, 3, 4, and then we have our column of zeros. All right, so really what we're getting at is that this is the same as saying x1 is equal to 2/3 x4, x2 is equal to x4, x3 is equal to 4/3 x4, and x4 is the free variable, which is always equal to itself. All right, so somehow out of this, we have to come up with the appropriate coefficients to balance this equation. All right, so x is going to be equal to x4 multiplied by those values, 2/3, 1, 4/3, and also a 1. So then the big question becomes, will these values make sense? Well, mathematically, sure. Now, again, I mean, I don't know how many times I have to say this. Chemistry is not something that I'll even say proficient in. Like, it's just, I mean, however I am in grammar, like, dial that back by like 2 letter grades, and that's where I am in chemistry, right? So I don't know a lot, but if we're talking about balancing, it just feels like maybe fractions probably isn't the best way to go. I'm just thinking about like a fraction of a molecule, fraction of an atom. Isn't that like splitting an atom? Isn't that like a bad thing to do? So maybe we want to have like whole number values.
Just verbiage-wise, this solution is the non-trivial solution to homogeneous system?
Correct. So I have license to choose any x sub 4 value I want because x sub 4 is a free variable. I can choose 1, in which case the weights of each of these would be fractional values. But if I can choose anything, why not choose something that's going to make it a little bit nicer? So, yeah, so let x sub 4 equal 3, or if you want, some multiple of 3. Really, any multiple of 3 is going to get it done, but generally, I mean, what we're trying to do is come up with a solution that's going to form a basis of an entire system. So the smallest possible value that'll get the job done is typically what you're looking for. All right? So, you know, it's kind of like I look at it like a recipe where the ingredients that are provided on the box are to make one thing of brownies, like one tray of brownies. I know what that recipe is. So now if I need to make 14 trays, I know what to do with that one recipe because that serves as the basis of all brownie production. All right? So I can only imagine that this is something along those lines. Because again, no good at chemistry. So we're looking at x being equal to 2, 3, 4, 3. So we know our weights, and so now we know our solution, all right? Because I need 2 of these, 3 of these, 4 of these, and 3 of these in order to have a balanced equation. Now I can double that all. I can apply any scalar multiple I want to this. I can multiply it by 10. I mean, it'd be a little overkill to say I need 20 of these, 30 of these, 40 of these, and 30 of those, but that's still technically correct. So 2, 3, 4, 3 is the smallest possible whole number values that'll work in this situation. So 2, 3, 4, 3. Now it's too tiny. All right. Because it is completely reliant on stuff that you already know, which is great. And then the transformations, and that's it. All right. This is page 23. All right. So Definition of linear dependence and linear independence. That's textbook definitions. It's really, I'll just kind of weave my way through this, but it really comes down to the procedure, because that's where things start making sense, all right? Because, I mean, you read this, an index set of vectors, B1 to BP in vector space R, is said to be linearly independent if the vector equation equals 0, so homogeneous equation has only the trivial solution. Okay, so why didn't you just say that? You know, you have a homogeneous equation that only has the trivial solution. That is the case of a linearly independent system. All right, so I took the liberty of translating in the language sense, not the mathematical sense, into this area down here under the procedure. Because all of that stuff is really, I mean, it's just on and on and on, talking about the same thing over and over again. Process is to form a linear equation in the homogeneous system, and then solve that homogeneous system. And if you only get the trivial solution, then you're dealing with independence. If you get a non-trivial solution, then it's dependent, all right? Now, the trivial solution is just a column of all zeros. All right, so anything other than that, you have dependence. All right, it's just a question of dependent on what? Dependent on x4, dependent on x5. We've actually been working with this a great deal already. So there's really nothing new here, which is why we can talk about it right now. All right, so I did a solved example here. The question is, are V1, V2, and V3 linearly independent? So write it as a linear combination. Homogeneous system, right? So we're defining it as a homogeneous system. That's the important thing. We're setting it equal to 0. If the result is only the trivial solution, so you go through the row reduction technique and only come up with a trivial solution, then you're dealing with a linearly independent system, all right? And that should actually make sense based on the fact that, I mean, we haven't really done too much with 3 dimensions. We've touched on it a little bit, but the reality is these values form the basis of 3 space, all right? 1, 0, 0 along the x-axis, 1 unit along the y-axis, so 0, 1, 0, and then 1 unit along the z-axis. Every vector in 3 space could be defined based on this set of vectors, all right? So the question is, are they independent of one another? Well, according to this, yes, all right? So then another solved example, this forms the basis of another system, you know, some just fictitious system, all right? So same idea as a linear combination in matrix form, set equal to 0 with row reduction, RF in your calculator if you want. I would imagine that that's probably the way that you would go rather than doing it all by hand. You come up with this with some value t representing the multiplier, right? It's defined in terms of one or the other variable. But the bottom line is you're coming up with something other than the trivial solution. You're not getting 0, 0, 0, all right? So that's the case of linearly dependent. So that's really all there is to it. Like, you solve it. If you get the trivial solution, it's independent. If you don't, it's not. So let's do one together and then go from there. Maybe 2 together. Determines the vectors are linearly independent and justified. The justification is the RF, so that's not bad. So I could write it as a linear combination first. So C1 or X1 or whatever one, it doesn't really matter. I would go through the whole thing of saying, back in my day, I had to do all this by hand, but I don't even remember learning this in linear algebra. It was definitely a topic that was glossed over. I remember him talking about one-to-one functions for the better part of the semester, though. We'll talk about that for like 20 minutes. Just out of spite. All right, so edit. You go 3 by 3. Just remember to put the zeros in, or 3 by 4. If you're worried that, like me, you'll forget to put the zeros in. Alright, so you get your values in. And if you're not taking another math class, you just hit second enter or the up arrow, because odds are RF A is in there somewhere. You don't even have to go looking for it. Look at that. The only challenge when it comes to these kind of questions is knowing what you're looking for. Once you know that, you're kind of unstoppable when it comes to this. This is supposed to be bless you. It's supposed to be a gimme. Like on a test, it's supposed to be a freebie. Because from this, I get C1, 2, and 3 are equal to the 0 vector, which is the trivial solution. Therefore, the vectors are independent. Vectors linearly independent. Trivial solution, that's the end of it. Linearly independent. Yeah, just phrase it the way the question's asking, because sometimes it'll say determine if the system is linearly independent. System, vectors, whatever. I'm not going to lose too much sleep over it. You know, if you said system and the question said vectors, it's not the end of the world, but just for a little element of precision, that's probably not the worst idea in the world. For number 5, A should have more room, but it does not. And so that is a typo for somebody, if you are in the market for one of those. So these are good questions in the sense that they're asking us for the values of H, you know, it's an unknown, that'll make it a linearly dependent situation, but also they want to know what values of H would put it in the span of V1, V2. All right, so let's develop a linear combination that's going to allow us to prove whether or not V3 is in the span of V1, V2. That should sound kind of familiar. So C1, V1 plus C2, V2 should be equal to V3. C1, 1, negative 3, 5. Negative 5, that is. My penmanship got a little out of hand here, so I'm just going to tidy that up a little bit.
It's just V3, not C3, V3.
It's just V3. All right, so in this case, using row reduction techniques, hence the mentioning of space being required. Plus. We want to try to get this down into reduced row echelon form and then see if we can get H to be some particular value that allows for a solution to exist. All right, because we need a solution to exist in any capacity. It doesn't matter what the solution is as long as it exists, and B3 would be in the span of B1 and B2. So any kind of solution, all right? But for B, in order for there to be linearly dependence, the homogeneous solution has to not be the trivial case. All right, so that's it's a different task. So it's a different approach that we have to take. And unfortunately, not something that's overly calculator ready. So this is not a just write ref and call it a day. So we could bang out here both elements in the first column below the 1 just by doing a 3R1 plus R2, and then also simultaneously a 5R1 plus R3. So 0, that was the whole point. Then if I multiply, so this is kind of a nice byproduct. Doesn't always work this way, but if I multiply -3 by the 3, I get a -9 plus 9 is 0. That's beautiful. Three times 2 is 6, plus the -5 is a +1. That's nice. All right, multiply by 5, we're going to go to 0 there. We're also going to go to 0 here. And then for the last one, we're going to have 5 times 2 is 10 plus h. So 10 plus h. All right. So it was actually a short trip because what we're dealing with here, we have a pivot value in the first row, and we have another pivot value in the second row. I mean, I could reorganize some things, but one way or another, I'm going to have a pivot in the last column if I'm not careful. All right? And so, actually, that shouldn't have worked out that way.
Isn't that your solution?
That would be no solution.
Because 0 is canonical too.
Yeah. Hold on. Let me just check my arithmetic real quick. No, that is what it is. That's not what I had in mind, though. It's supposed to be more powerful, startling realization.
Can't you then not solve for h? Because
Yeah,
the system isn't-
no, it's irrelevant, yeah.
It's
One of those. I'm just making sure I wrote down everything correctly first before I scrap this problem. 3. What are you gonna do? Half the class raised their hand. So
Would it not be worth it to treat it like a homogeneous system and set your solution vector as 0?
that would be showing that there are weights that would allow V1, 2, and 3 to yield the 0 vector, which is what the independence is really showing. So it's really kind of strange because I don't remember this problem ever not working, which means that that means that I've repeatedly screwed this problem up. We're not seeing any mistakes, right? Except for the structure of the question itself.
The agent and put everything to equal to 0 vector.
Yeah, that would be the same idea. Yeah, because V3 has to be in the span of V1 and V2, so this is the only way that you could set it up. Yeah. Okay, so I just changed the problem to say if any, and therefore no solution. Kev, what's up?
Wait, is this for part A or
For part A.
Oh, okay.
Part B we're going to do it in a second. All right, so part B, a little bit more straightforward on the setup, because that's what we've been doing before, all along. One, we'll just jump right to the homogeneous setup. 1, -3, -5, -3, 9, 15, 2, -5, and H. And then we'd have the 0, 0, 0. So same approach. We have to row reduce. The good news is, I mean, if you can assume that that's a thing at this point, 3R1 plus R2 and 5R1 plus R3. That's still going to be our first move.
What if we put A to the calculator as X?
Well, X is stored as a particular numerical value, so it's not going to treat it as a variable. It's going to actually plug in a numerical value for X, and it'll screw everything up. So I can steal my work from the previous part. That the only thing that would be obviously concerning would be as if I made a mistake there, but I'm just going to choose to believe. So this one has the 0, 0, 0 on the outside. So it's still the same steps, just now we're not getting the no solution component, because really there's no way to get a pivot value in the last column. All right, so we're either going to get a particular solution, or we're going to get a general solution containing just a 0 vector, or something's got to give at this point. All right, so it's just a question of what that's going to be. All right, so we're looking for linear, again, dependence. All right, so anything that I come up with that allows for us not to end up with the trivial solution is going to be sufficient. All right, so I just want to make sure that I have everything reduced the way I want it to be. All right, so I have my pivot value in the first row, I have a pivot value in the second row. Now, if we're going to have this be an appropriate solution, well, if this is my pivot in row 2, to have a row, have it in reduced row echelon form, the 2 and the 10 plus H would have to go away. All right, so there's a couple of ways I can handle that. I can define the H right now, or I can do the row operation that'll simplify that for me. So, for example, in this case, I can just do a quick negative, that's supposed to be purple, -2 R2 plus R1. That's not going to change anything in R1 except for the 2. which is going to become a 0. So 1, -3, 0. Row 2 is perfectly fine the way it is. But then I have my 0, 0, and 10 plus h. Okay, so at this point we can kind of call it, because I can start drawing up my solution. I'm going to circle my pivots.
I'm sorry. If you're doing -2 or 2 plus R1, shouldn't your second row then be 1, -3, 1?
My second row?
Yeah,
Your
negative.
second row was 0, and then you're adding row 1. So
Adding a 2 row 1.
adding it to row 1, but with, oh, you're changing row 1.
Yeah.
Thank you.
No.
All right, so I can define this in terms of my -3.
So now I just got to remember what my original variables were. So C1, I can now state that C1 is equal to 3C2. I can state that C3 is equal to 0. I could state that C2 has to be a free variable because C1 is defined in terms of C2. But the only way that this is going to work out is if this value here goes to 0. So what value would h have to be in order for this to go to 0?
-10.
H would have to be -10. So assume h equals -10, in which case you get
A complete wipeout on the bottom row, and that's our free variable.
so we're in good shape there. So C, and actually at this point you're even done. Because once you define, because you don't have to go, like, this is a test taking strategy. You don't have to go the distance and write it up in terms of a final answer. Once you define one variable in terms of another, that is linear dependence.
How about C2?
Yeah, C1 is defined in terms of C2.
All right, it's not the trivial solution. All right, so once that happens, you're done. You would just need to state the h value that caused that to happen.
All right, or at least allowed you to go the whole way.
It doesn't matter what the value of h is, since C1 is determined by C2. No?
Right, but if this is something that's not, like, let's say it's a 2, like, let's say you made h like a -8, then that would become a 2, and then you'd have to perform another operation to get that 2 to go
Oh,
away.
right.
So it's the most convenient value is h equals -10 in order to make this like your last stop, and you don't have to do extraneous work.
All right. But, you know, if you wanted to continue on, you could say C2 equals C2 and then create your solution vector. But like I said, it's not really necessary. I'll write it down for you just so you have it. But you would stop here because you've finished the task. C2 is equal to C2. So C3 could be thought of as 0 times C2. You just got to keep the ordering straight. So C1, 2, and 3. Those weights would be C2 times 3, 1, 0. Yeah, because these are in reverse order. Super duper easy.
And I'll show you what I mean by that. All right, so 30, I believe.
Yeah.
So
We're starting with, and we're only going to work in 2 dimensions for now, or at least in this unit. We have the identity matrix. Identity matrix 1001. Up until this point, really it's just been a matrix that was like, okay, it's got ones and zeros in it. Why is that important? Because it's simple. We want simple. All right, but it's more than that. All right, if I were to graph each of these vectors, I get the unit vectors on the xy plane. So here's 1, 0. And here's 0, 1. All the transformation is doing is moving these points somewhere else. All right. So what we're going to do when we're doing a dilation transformation, for example, is we're just going to determine where these unit vectors will end up after that transformation. All right. And that's going to be the standard matrix, so that it would allow me to transform any vector using that information, right? Using matrix multiplication, all right? So dilation with a factor of 4. Now, if you think back to high school math, geometry, when you dilated, you multiplied. You multiplied the coordinates, both parts, by whatever the dilation constant was. All right? So that's what we're going to do here. So the coordinates 1, 0 will become 4, 0. The coordinate 0, 1 will become 0, 4. So the dilation matrix instead of having 1, 0, which corresponded with the coordinates, so that first vector 1, 0 corresponded with the coordinates 1, 0, we're going to use 4, 0. Instead of having 0, 1, I have my new coordinate, which corresponds to a new vector, 0, 4. All right, and that's your transformation matrix. So what that tells me is if I had a vector, so I'll just throw a quick example here. Dilate vector 2, 1 using matrix above. So all you would do is take your 4, 0, 0, 4 and multiply it by 2, 1. Now, this is just the skill of coming up with the transformation matrix. But really, I mean, you know how to dilate 2, 1. You're just quadrupling each value. It should be 8, 4. All right, so if you get anything other than 8, 4 when you do this calculation, then you did something wrong. You could do this calculation on your calculator. You don't have to do it by hand. But doing it by hand is not terrible here because we have the 4, 0 multiplied by the 2, 1. So 4 times 2 plus 0 times 1. And then 0 times 2 plus 4 times 1. Giving us as a result 8, 4. All right, so anytime you're looking to come up with a transformation, this is specifically related to dilation, but anytime you're looking to come up with a transformation matrix, all you're doing is deciding where your 1, 0 and 0, 1 would go after that transformation. All right, so in the next one, we're talking about rotating through the origin for some particular counterclockwise rotation for an angle. All right, so the standard matrix for that, you'd say, well, okay, what does that mean? All right, we're keeping it in general terms, but general terms is good for us here because this kind of sets us up for pretty much any problem that involves a rotation. All right, if I'm going out 1 unit in any direction, what I'm going to end up on is a circle. Anybody know what the name of that circle is? Yeah, it's the unit circle. Of course it's the unit circle. It's always the unit circle. Fill. I think I have to decide on the fill before I actually draw it. Well, whatever. Perfectly sufficient circle. All right. So it's rotating about the origin through an angle of phi with counterclockwise rotation for positive angle. All right. So phi, theta, whatever. It's a Greek letter. Who cares? All right. So the whole point is that you're going to take this vector, vector 1, 0, and it's going to rotate. Simultaneously, you're going to take this vector and rotate it by the same distance, the same angular distance. So that you come up with a new vector that would be here and here. All right, so we're working off of some arbitrary angle phi, but let's get specific. Let's let phi be equal to, I'll keep it simple, 30 degrees. All right? I want to make this clear and obvious that this is a unit circle situation. Do you know what the coordinates would be at this location, 30 degrees up? Based on the unit circle? Radical 3/2, 1/2. All right. Now, if I rotate this 30 degrees, my whole angle is 120. Anybody know that one? So negative 1/2 radical 3/2. This is what we call a red flag, folks. Well, I'll talk to you about the bonus in a minute, and that'll maybe help. All right, so when I'm coming up with the transformation matrix based off of this, I'm just asking, where did my 1, 0 go? And where did my 0, 1 go? After that rotation, 1, 0 went to radical 3/2, 1/2. 0, 1 went to negative 1/2 radical 3/2. That's the transformation matrix. All you're thinking about is where 1, 0, 0, 1 would go after the operation. All right, so now if I needed to find any vector rotated 30 degrees, I just have to multiply it by this. All right, so if you think like, all right, I need to reflect over the y-axis. Well, 0, 1's not going anywhere, right? But 1, 0 would become negative 1, 0. If I reflect over the x-axis, 1, 0 is not going anywhere. 0, 1 is getting reflected. It would become 0, negative 1. So all you're thinking about is transform the given values 1, 0, 0, 1, all right? So your identity matrix, transform that, and then multiply it by whatever vector you're looking to actually operate on, and you'll have it. That's what the tech assignment was asking you to do, or at least the second half. And so conceptually, there's really nothing more to it than that. The only difference is, in this case, they said that we're working in terms of phi. So if I want to let phi be a variable, so this is the only little twist on it. If phi is variable, then we're looking at cosine of phi sine of phi. All right, because on the unit circle, it's always, every coordinate is cosine theta comma sine of theta. So this would be my angle phi. The other one would be 90 plus phi. All right, so we'd be looking at cosine of 90 plus phi. And sine of 90 plus phi. All right. So, I mean, I'm not going to ask you anything like this on the test, but these values, these kind of questions are fair game. But if you know a little bit about the unit circle, it's no problem.
Why is it when we multiply 30 degrees, why do we get pi over the, I mean, radical 3/2?
Oh, because the cosine of 30 degrees is radical 3/2, and the sine of 30 degrees is 1/2.
It has to be the cosine of the.
Yeah, it's all unit circle stuff. All right. So I know I took us right up to the wire here, but I wanted to make sure that you had,